Welcome to the Quantum Gravity channel.
In the talk I will present a prediction for the tensor-to-scalar ratio in primordial cosmology, and that is an important quantity because it is one of the very first few quantities of fundamental physics that is going to be measured within our lifetime, probably. They say that the data will tell us its value in 10 years or something. This is the prediction. So it is in a window that is bounded by the expressions that you find in this formula that differ just by a factor 1/9, and ns is the tilt of the scalar spectrum that is measured already, so you can put numbers inside this prediction. But why is it, and it was derived with Bianchi and Piva in this paper. Why is it interesting? And we will see where it comes from, basically, because there is a connection with high energy physics. So this makes this kind of prediction quite unique, very constrained, and falsifiable. If it turns out to be wrong, then a lot of things turn out to be wrong and to talk about. And we will see in the talk other connections with high energy physics, sort of vocabulary between perturbative quantum field theory, renormalization, group flow, and inflation. And the reason is that when I started inflation, which I was not familiar with, I found very difficult to understand what cosmologists say, and so I tried to translate everything in my own language coming from high energy physics. So this prediction comes from a theory of quantum gravity with so-called purely virtual particles, or fake particles, or phacons. And they are particles that cannot be on shell. So normally particles can be on shell or off shell, virtual. And you cannot have a particle that is always on shell. That would be a purely classical thing. You cannot have it, you don't have it. Maybe you could, but I don't know of any examples of that. We do not know of any examples of that. Instead, what about a particle that cannot be real, can only be virtual? And you have to find a way to make room for it inside diagrams, because such a notion needs a new diagrammatics, basically. And I will present this new diagrammatics in the beginning of the talk, because you have to be sure that you do not destroy the basic principles of quantum field theory. Renormalizability is not in question here, but unitarity is the delicate thing. And because this thing comes from high energy physics, from the same path that led to the standard model of particle physics, it's quite unique, very constrained. You cannot even choose the inflation mechanism. There is only one. It is the Starobinsky one. And you have corrections that modify the prediction, and we will see how to treat them. Pretty much like the standard model is very constrained by unitarity, locality, and renormalizability, the same here. So this prediction is very sharp. If you put the numbers that I mentioned earlier in the prediction, in the formula that I showed before, this is the prediction, and it is basically one order of magnitude away from the present bound, experimental bound on the tensor-to-scalar ratio, which is the ratio of the amplitudes of the two perturbation spectra, the tensor one and the scalar one. I will not talk about other applications of the notion of pure virtuality, but there are in phenomenology, which we have explored here in Tallinn, and they could be used to propose models for new physics beyond the standard model to solve discrepancies with data and so on and so forth. You have to admit, however, in this case that lighter, purely virtual particles exist. In gravity, you just need one, we will see, and very, very heavy. The mass would have to be heavier than 10 to the 13 GeV. And it is also possible to, we will see this in the final part of the talk, reformulate inflation as a renormalization group flow, where the spectra are seen as correlation functions, which satisfy Callan-Symanzik equations. And this allows you to compute high-order corrections to the spectra in a systematic way. Not always. You cannot translate this. You cannot use this to translate every inflation mechanism you have, but only a subclass. And it does work for the one that is incorporated in the theory of quantum gravity that I'm going to talk about, which is the Starobinsky one, basically. But it doesn't work in general, so there is a certain classification. So in the first part of the talk, I will present how the new diagrammatics work. And this is also a general result that you can apply to any quantum field theory without even thinking about purely virtual particles. Just the usual Feynman prescription. You can turn basically unitarity into pure algebra, because unitarity is a very difficult thing compared to the very simple recipes that we have for locality and renormalizability. But you can turn it into pure algebra by means of a trick that I will show you. And you can decompose the optical theorem in several independent identities that allow you to play some tricks that are useful if you want to define new types of diagrammatics. And we will see explicitly the bubble, the triangle, and the rest can be seen in the paper. Then we will discuss the difference with respect to, for example, stellar theory of higher derivative gravity, the Leavitt models, and this will introduce us to the cosmological part, because the difference is crucial to illustrate the cosmological applications of this. In the second part of the talk, we will talk about primordial cosmology and inflation reformulated as a renormalization group flow. We will discuss how to make the y squared term in higher derivative gravity purely virtual. And to make the discussion easier, we will start from two toy models from non-relativistic mechanics, where everything can be understood quite clearly, and if you want, you can repeat the exercise by yourselves with no effort. Then we will see what you have to do to define pure virtuality on a non-trivial background. This is the new ingredient of cosmology, because from high energy physics, you just have flat space. So there is something new that you have to consider here. And that is what generates the prediction, by the way, the sharpness of that prediction. And then we will see how inflation can be reformulated as an algebra flow with the Callan-Symanzik equation for the spectra. And then we will conclude with some high order corrections that will probably never be measured, but it's interesting to know that the theory is so constrained that it can predict things that we will never be able to measure, probably. So let me start from very simple basic notions. These are propagators, various possibilities. This is the propagator of a standard physical particle, and you can decompose it into a purely virtual part, which is the principal value, and then there is an on-shell part. This is the particle, the real particle. Then you can consider a ghost. A ghost is the same thing multiplied by minus, and then you have the purely virtual part is negative, and what's important is that the on-shell part is negative. So basically this is like a -1 particle. You are violating the optical theorem already at the tree level. Then Leavitt proposed a certain construction where you can make this kind of object, you can treat this kind of object in a theory where you change both signs. You cannot use this propagator like this. You have to supplement it with suitable rules to treat the diagrams. And because this is delicate if it is present together with the opposite prescription. But at the tree level, you will have again something with a good sign here. And still there is, you see in a Leavick so-called ghost, there is an on-shell thing. What is a purely virtual particle? It's a particle where you do not have anything on shell. So you just have the principal value, and what I'm going to say will work for both signs. So you have two possibilities. You do not have a possibility to change the sign here. So that will always be crucial for us because it will impose no tachyon conditions, and ultimately the no tachyon condition in cosmology is the bound, one of the bounds on the tensor-to-scalar ratio. Okay, so before giving the details, let me remark that in the two cases, the two last cases, Leavick and purely virtual, you need to supplement these propagators. You cannot just use those propagators inside diagrams. You have to give rules to define the diagrams, and I will give the rules in the purely virtual case. Because otherwise, if you have diagrams with both plus I epsilon and minus I epsilon, you can check this paper, you will have many problems. You will have exchanges between thresholds and pseudo-thresholds. You will violate the locality of counter terms. You do not even have a good power counting because you have residues in the wrong quadrants, and so you cannot even make a Leavick rotation. You can, but you will have unphysical results. So you must treat those things properly. Let's see what you do in the case of purely virtual so-called particle. So basically, at the tree level, you just drop the on-shell part. And instead of this propagator, possibly with two signs in front, you just have the principal value. However, you cannot use the principal value inside diagrams. What do you do inside diagrams? Well, basically, you can do, so to speak, the same inside diagrams. The point is that you should not use this decomposition, but you should first integrate on the loop energies and then use the decomposition. This is crucial. So this is the procedure. The first thing here is important because it tells you that you should ignore the integral on the space components of the loop momenta completely. So you will have a theorem, a set of theorems and identities that are valid without integrating anything. They are valid on integrants. They are algebraic. You do not need to integrate on this thing. That is something that makes things very complicated. You just integrate on the loop energies, and this is an algebraic operation because you use the residue theorem. So it's not an integral, it's just an algebraic manipulation. Only the loop energies. Once you have done that, you can apply the decomposition. There are caveats from the box diagram, which we will not discuss, but this is the crucial decomposition. We will see the bubble and the triangle. And then you drop all the deltas that contain frequencies from the particle that you want to quantize as purely virtual. That's it. Let me show you how it works with the bubble. The bubble is an integral with two propagators. You forget about the integral on the space components of the loop momenta, so you just integrate on the loop energy K0. I use different prescriptions, epsilon 1, epsilon 2, because I want to be general for the two legs, different masses, different external momenta. One is sufficient, but I want symmetric formulas, so I introduce redundant external momenta, one for each internal leg, just to be symmetric. So and I multiply by 2 omega. This is to simplify the result. So the diagram will have not this factor, and it will be integrated on the space components of the loop momentum. So you integrate on the energy by using the residue theorem, and you find 4 contributions, but 2 of them mutually cancel. This is the crucial good thing of the Feynman prescription. Those that cancel are those that have differences of frequencies, which would be instabilities. They cancel, they just disappear, and you have only 2 contributions which have only sums of frequencies, you see. With the correct prescription, epsilon here is the sum of the 2 epsilons, and E1 minus E2 is the external energy, the incoming energy. So now you decompose this thing with the identity written here. And you find 2 contributions that are purely virtual and 2 contributions that are on shell. And that's it. This is the bubble. So if you want to quantize one particle 1, for example, as purely virtual, you check when the frequency 1, omega 1, appears in deltas, and you drop them, both in this case. So there is no difference if you have 1 purely virtual particle or 2 here. Let me describe these operations in a table. This is the diagram I just showed you. This is the bubble. In vertical you have the various contributions. There is a purely virtual part, which is the principal value, a sum of 2 terms. And then there are 2 deltas, which are written here. And why do I use these columns and different rows? Because then I do the same not just for the diagram, but also for the complex conjugate diagrams and the so-called cut diagrams that are useful for the optical theorem, which is a way to express the unitarity equation. And it is basically the statement that the sum of these diagrams is 0. And what is the content of the optical theorem? It is just this. And what is the content of the cut diagram? Basically, a cut diagram is a diagram where you cut internal propagators, and that means that the virtual particle propagating inside becomes real. So you have the physical process associated with this virtuality becoming real. And that means that the cut diagram tells you about this. So it is useful to do the same decomposition and the same operations that I described earlier on all the diagrams and put them in the table, put the contributions vertically like this, because you will see that you can decompose the identity, sum of this equals 0, in several different independent identities. Each row is 0. That's the crucial thing. And so if each row is 0, when you want, for example, to make a particle 1, purely virtual, you throw away the entire row where you have frequency omega 1 inside the delta. This is the delta. And you have to throw away 2 rows in this case, because if you throw away an entire row, you are sure that you are preserving the optical theorem, because the sum of the entire row is a 0 in the optical theorem. So that's why you can preserve the optical theorem by means of these operations. And you have to do them consistently in all the diagrams of your theory, of course, because otherwise it's not consistent. So basically, when an internal particle is fake, these 2 rows disappear. But then you realize that there are 2 diagrams that disappear completely because only zeros remained. You can remove them, so 2 columns disappear as well. And this is reasonable because if one particle here you want to be fake, that means that it cannot be brought on shell, so its cut propagator should be 0, and so the entire diagram should disappear, and that is okay. And so in the end you remain with these 2 contributions, and that's it. For the bubble, that's it. And the optical theorem is still valid because the sum of these 2 is 0. If you go to the triangle, it's the same. An integral of 3 propagators. You have a purely virtual part, which contains only principal values, and then you have 6 terms with 1 delta and 1 principal value, and 6 terms with 2 deltas. And then you do the same for the complex conjugate diagrams and all the 6 cut diagrams. A little bit of patience, you will fill this table. And then you will see that every row sums to 0 separately. So you don't just have the optical theorem, which is that sum of diagram equals 0. You have a decomposition of that into different identities because every threshold is independent and should independently sum to 0. So what happens when, for example, particle 1 is fake? You have to eliminate all the rows, the entire rows, where you have a delta with an index 1. That means that you have a frequency 1. So only delta 3, 2, 2, 3 disappear. But then you see that when you eliminate the red things, some blue columns get only zeros. This is okay. 0, 0. And disappear. So you eliminate them as well. And the corresponding columns are those where the fake particle is cut, which should give 0 because it cannot be brought on shell. And so this is how you get the diagrammatics of the purely virtual particle propagating inside with its diagram, its conjugate diagrams, and the only surviving cut diagrams. And in total, you still have the optical theorem. So this is the versatility of this method. I want to show you the difference with respect to the approach of Lee and Vick, because in a recent paper I pointed out the difference, which is crucial because Lee and Vick they had very nice intuitions about ways to give sense to theories with higher derivatives. And then if you have higher derivatives, of course, you have what they call abnormal particles. But then they say it's important that you do not have stable abnormal particles, because if they decay, they do not belong to the S matrix, which is concerned only with the asymptotic states. And they list the stable states, forgetting the muon, because of course the muon is unstable, and we do observe it. So the approach of Lee and Vick is kind of physical in some sense. They want to remove states because they acquire a width and so they decay. They want to remove a degree of freedom physically. But then if you remove it physically, and this is crucial for cosmology and primordial cosmology, we will see, then you cannot remove it completely. Instead, I remove it mathematically, let's say. And an example that was the inspiration for this, which does not apply, is just the example of Fadeev-Popov ghosts. That is what you should keep in mind, or the longitudinal photon, because A mu has 2 extra components that are not physical, and then you have the Fadeev-Popov ghosts and anti-ghosts. And you have a mathematical projection that allows you to show unitarity but after getting rid of all of them. And that's why you know that it works. But you can say, okay, but that works because it's a symmetry. It's protected by a symmetry, the gauge symmetry. So the game was, okay, but can I make it work without a symmetry? Can I find something else that protects the entire thing? And the something else is this set of identities into which you can split the optical theorem. And this is important for cosmology. We will see in a moment, because, as I said, if you remove something physically, there is always a place where it is not removed. For example, if it decays, you could try and observe it before it decays. And in cosmology, that's precisely where you get into. And because in primordial cosmology, you basically have to take the classical limit of your theory, and then you quantize the classical limit. But in the classical limit, every width goes to 0, because it's an h-bar. A width has an h-bar in front. So every particle is stable in the classical limit, because particles cannot decay classically. Okay, so these are some papers where you can find recent works on these things, like Lee and Vick or the muon, and a review. Okay, so this difference with respect to the Lee-Vick approach, for example, and purely virtual particles is crucial for cosmology because of the reasons that I have just said. And then there is another thing. This I say because some people from high energy physics do not appreciate the crucial difference between high energy physics and cosmology. You cannot, in high energy physics, ignore massive degrees of freedom. Because normally in high energy physics, if something is heavy, you say, okay, I do not need heavy things for predictions about low energies. And what you are interested in cosmology is the super horizon limit, super horizon scales, which are kind like infrared, low energies. And then you can say, okay, but I can neglect the massive things. That's not true, because in cosmology you have to first assess properly the sub-horizon scales, like with some condition, the Bunch-Davies condition, for example. And the reason why this condition is disputed is precisely that it is a condition about the sub-horizon scales, which are by definition out of reach. We will never be able to reach them. So only if in that limit you have something as simple as a scalar, as simple as a harmonic oscillator with a constant frequency, you might bet that the usual quantization of a harmonic oscillator with a constant frequency is the right condition, and this is the Bunch-Davies condition. But still, there are people who do not buy that. So, however, if you have a ghost or a living ghost or anything that is awkward in that limit, of course you cannot make this sound equally robust. And in this case, in the case of purely virtual particles, we will see what you have to do. You do not have these issues, but still you have to be sure that these purely virtual particles are purely virtual at all energies. This is not an issue in flat space because it's flat, but in a non-trivial background, and here in cosmology we have a non-trivial background, this is crucial. So pure virtuality should be pure virtuality even in the sub-horizon scales before making predictions about the super-horizon scales. So we start from this classical Lagrangian, but this will not be the classical Lagrangian. Again, this is a starting classical Lagrangian. It's more or less like the gauge-fixed Lagrangian that you can use for many purposes with ghosts, but you don't treat it like a classical Lagrangian. You have to make some projection to go to the physical Lagrangian. Here, the same. And I will describe with some toy models from non-relativistic mechanics how to make this projection. So if you analyze the expansion of this, I drop the cosmological constant just because it's unnecessary in cosmology, but otherwise you should add it for renormalizability. If you expand around flat space, then you will see that you have 3 degrees of freedom. One is the graviton, one is the inflaton, and the mass is here. And one is the spin 2 thing that will have to be quantized in a new way so that you make this purely virtual in some way. And I have already mentioned that you can make sense of propagators with both signs in front, let's say fake on prediction, prescription, but you cannot change this. So you should be sure that you have no tachyons. And in flat space, the no tachyon conditions are just the 2 signs here. So the 2 signs here cannot be changed. But as I said, this is not the classical Lagrangian. It's just the starting, let's say, like a gauge-fixed Lagrangian. The true action will have to be the collection of 3 diagrams where the fake particles is only inside and not outside, and how to propagate it inside by means of its own prescription, because you cannot choose boundary conditions for this. It is purely virtual, so it doesn't even get to the boundary. It's useful to introduce a scalar field explicitly, the inflaton, and we will still keep instead the Weyl-squared term in its original form. You can eliminate that and introduce the spin 2 massive particle, fake particle explicitly, but that would not make the calculations easier. It will make them very, very complicated, so it's better not to do it. But this is something you can introduce explicitly, and in this theory you just have the Starobinsky mechanism for inflation. You cannot change it, And so high energy physics prefers that. And the equations of the background, Friedmann equations plus the equation of the scalar, are the usual ones because the y-squared term doesn't change them. The Friedmann-Robinson-Walker metric is conformally flat, and so you can show that the background doesn't change. And instead, the presence of y-squared changes the predictions for the perturbation spectra. So let me show you where to get to the right classical theory, because again, this is not the right theory, classical or quantum. In particular, it is not a right classical theory. We will parameterize the fluctuations as usual. So this is the background metric, and then you have the two tensor polarizations, U and V. Then you have the scalar thing. We will concentrate on U. V is the same, and the scalars are more complicated. So to make things transparent, we'll just treat tensors. And this is the prediction. Before telling you how it is calculated, this is just the list of things that you can compute to the lowest order. This is quite standard. You can use every method you want, but the important thing is the bound that we will have on the mass m chi, because otherwise the prediction allows you for a wider range of values for the tensor-to-scalar ratio. So I repeat the notation. M phi is the inflaton mass, which is, by the way, something that we can derive from the measurements that have already been done about the scalar spectra. Ns or Nr, I also called it Ns, is the tilt of the scalar spectrum. Ar and At are the amplitudes of the scalar and tensor spectrum. Ar is measured, At is not. N is called the number of e-foldings. I don't like to use N, but I used here just because people normally use it, but we will see that there is a better, for me at least, better way to formulate everything in terms of a fine structure constant of inflation, so-called a coupling, which replaces in this RG flow formalism the slow roll parameters. And then yes.
Can I ask a question? Yeah. So you started explaining about Facchion prescription for Minkowski spacetime. Then you now jump to cosmology. So my question is about whether Facchion remains as a Facchion in the cosmological background.
Yes, this is what we are going to discuss now.
Okay.
But first I give you two examples from relativistic mechanics to appreciate the points. And still they are in flat space. So the no-tachyon condition that we will find from this new thing that you have to work in a background now, and you have to define a facon in the background, is this. We will see where it comes from. And the prediction that I told you about already is this one, numerically. And this one, I don't know if we will have the chance to see the tilt measured in our lifetime, but at least they promise that we will measure this. Okay, so the crucial thing is how to treat higher derivatives. And to clarify the procedure, I start from classical non-relativistic mechanics, flat space, and then we will gradually move to the crucial point. This is a simple model where you have the standard kinetic term and a standard harmonic plus anharmonic potential. And the non-standard thing is that I add some higher derivative terms. Okay. I want to tell you what to do this in this Facon approach. First of all, write down the equations of motion. To the right you have x cubed, and to the left you have the quadratic part, which is linear here, so you decompose it into two oscillators, and the two frequencies are written here. Lambda tilde will be lambda divided by m. And to have a no-tachyon condition, let's say, to have real frequencies, big frequencies, real, you impose this condition on the small frequency, starting one, omega, so it should not be too large. Your oscillator cannot oscillate too quickly, basically. So this is important just to show you that there could be, and there is also in cosmology an additional condition that you first have to satisfy. Once there is a condition, then you proceed as follows. I do the calculation with no harmonic part, so omega is 0, and this is always satisfied, just to simplify the formulas for the top, because you do not lose any crucial point. So this is the equation of motion. What do you do? Simple exercise that you can do by yourselves. You write down the most general equation of motion with no higher derivatives, or Lagrangian with no higher derivatives, or Hamiltonian or energy with no higher derivatives. Just do the following thing. You write down for the Lagrangian, for example, the most general expansion in monomials of x and x dot with no higher derivatives. And the same here, just x2 dot equal to the most general expansion in x dot with arbitrary coefficients. And then you take your expansion with arbitrary coefficients, you write down the equation of motion from this Lagrangian, you put it here, and you demand that the original equation of motion, the higher derivative one, be satisfied, and you will fix all the coefficients perturbatively. And this is the unique answer. So you can ask, where is the famous Ostrogatsky instability? Well, the interesting thing here, so this is a perturbative expansion that you can write. Perturbative in what? It is perturbative in this coupling lambda tilde. It's not a low energy. It's not just low energies. You do not need to expand in tau separately. Just expand in lambda. But you will find a unique answer. The point is that if you continue higher corrections, the coefficients here will start to grow. You just already see it, and explode. And basically what you can have this way is only an asymptotic series. So you will have to take the original Lagrangian, the higher derivative one, which, as I insisted several times, is not the classical theory. And your classical theory will be this one. You modify the theory, basically. But then this is true. It has no higher derivatives. But you do not know the exact expression, which would be some exact Lagrangian out of which you would have this asymptotic expansion. And from the asymptotic expansion, you cannot resurrect the Lagrangian it comes from. So probably you cannot say anything about the Ostrogatsky instability because this is perturbative. And you have a perturbative expansion. And the novelty with respect to normal things is that in quantum field theory, normally we have asymptotic series all the time, but normally only in the solutions, not in the equations, not in the Lagrangian. At least we have a closed form of the Lagrangian. And in this case, you cannot have a closed form of the Lagrangian. The Lagrangian itself, the classical Lagrangian itself, is an asymptotic series.
Sorry, may I ask you a short question?
Yes.
I'm just curious, what happens if lambda is equal 0?
If lambda is equal 0, here you have just the starting. You have the two things are decoupled, so the projection is just the removal of the fake part. So you just have, in this case, you just have the oscillator with 0 frequency. But if you have a non-zero frequency, you will just have the free harmonic oscillator, just one.
So you mean if lambda is equal 0, you're just saying that I have to just remove one particle by hand?
Yes. No, it's already removed. If you take this and put
if I take this, I know, but I can, with lambda equal 0, I can easily solve the initial equation without introducing this.
Yes. If you
and I know that there is classical instability.
Yes. If you have the original thing with lambda equals 0, you have two oscillators.
Yeah.
Okay? And the Facon prescription is that you have to solve the second oscillator with the Facon prescription, but the equation of the second one, which I will in a moment call Q, will be certain operator times Q equals 0, and the Facon prescription gives you a unique way to say what this operator is to the minus 1. But since it multiplies 0, that's what you get. So the projection is trivial when there is no interaction.
Okay.
Again,
I'd like to ask a question too.
Yes.
First, a comment. This is a technique that has long been known. It's called perturbative localization. And what typically happens when you do it, because you have to make a distinction between time derivatives and space derivatives, is that the resulting series that you get, in addition to being asymptotic, also breaks manifest Lorentz invariance. How do you avoid this?
I do not see here any violation of Lorentz invariance, because this is completely
maybe I wasn't clear. If you're talking about a point particle theory, but if you did it for a field theory, you would of course select out the time derivatives special, right? So the Lagrangian and the equations would still continue to have higher space derivatives, but no higher time derivatives. Like I say, this is a well-known technique called perturbative localization, and what typically happens when you do it is that you break manifest Lorentz invariance. How do you know that you avoid that?
Yes, I do not break time derivatives and space derivatives. I do everything explicitly in a Lorentz invariant way, even in gravity. I will not show you in cosmology because unfortunately there is only time there too, but I can point you to...
I don't think that that's generally possible. I think that generally, in order to localize, all you can do is localize in time. You cannot get rid of higher space derivatives.
Here I have, instead of this, what you have is just the principal value of this in Fourier transform. So it's like something like the principal value of 1 divided by box plus m squared.
But metrics have indices, right? And there are going to be things that involve space derivatives of things that are not going to go the same way. It isn't all going to be products of del squareds.
Yes.
Well, you're just denying that the problem that I asserted exists, yes, and I don't want to interrupt your talk, so why don't I just postpone this till later?
Yes, we can postpone it because I didn't find it in gravity. So if you take this Lagrangian and you treat it as it is an asymptotic expansion, you plot, for example, the solution. So we have no frequency here, just a Weyl, an harmonic, but you still have oscillations. And you can numerically study the solution. You will see an oscillating behavior, and this is the behavior you find if you truncate to the first order. If you go to the second order, you find this. And then if you include higher orders, you find the continuous line up to order 9 with a coupling equal to 1/10. And this is just to illustrate to you what happens when you manipulate asymptotic expansions. And after, if you continue with the expansion, it will blow. You will find a graph that has nothing to do with a correct approximation of your exact solution. So typically with asymptotic expansions, and you can check it numerically here, you find that the first few orders capture the properties of the exact solutions, and then you cannot decide how precise you want to be because the asymptotic series decides it by itself. However, we have to still check whether the projection is consistent, and the thing is not just about this expansion, because this expansion is applied once you know that you satisfy the right conditions to make it consistent. So let me go to the other point, which is crucial for cosmology. This is the propagator, the principal value, which is the sum of Feynman and anti-Feynman. By the way, this is Lorentz invariant, Lorentz covariant, and in all cases, even with indices, you will have Feynman plus anti-Feynman in the tree limit, however.
That's simply not true. Look, this is very well known. I've done it many times. Many other people have done it as well. You do break Lorentz invariance.
Okay, I will check that. I don't believe that. And if you restrict to time, this is the basic Green function. This thing in Fourier transform. So it is a sine of a modulus. Now in cosmology that is enough. So if I illustrate this with another toy model, which is the same but now with an external force, instead of the 5⁴ interactions, and you introduce an additional scalar explicitly, quadratically, so as to eliminate the higher derivative terms, just the usual trick, and you have two equations, then you solve the second equations with the Fécond prescription, which is unique again, and it is this sine of the modulus. You insert it here, and you find the projected equation for x dot dot. Okay, let's do this in cosmology. You insert the expansion in your action. I will concentrate only on this tensor mode. And you will find this higher derivative Lagrange. This is the part that comes from Einstein, and this is the part that comes from Weyl squared. You have the square of the second derivative, and the rest is okay. You call it a name. Okay, what do you do here? You can introduce a second scalar by adding a 0. This is equal to 0 because it's a new field and a square, and y is whatever you want. So if you add this thing, the u field equation kills the entire term that you added, and you use the trick as usual to get rid of the higher derivative terms and exchange the higher derivative terms for two fields instead, small u and big U. So what you get is something like this. After another simple redefinition, you have two fields that now are big U and big V. One has the right sign and one has the wrong sign. Okay, so this is the starting point. What do you do here? So you insert the ansatz to make this projection. V is an expansion in powers of, by the way, there is an alpha here. They probably didn't introduce. Okay.
Damiano, I'm sorry to keep interrupting, but you're losing me. Are you talking about the Eddington term, the extra derivative, higher derivative associated with the Eddington term, or are you talking about the extra derivative associated with the Weyl term?
Weyl squared term.
The Weyl squared term. Thank you.
And alpha is the slow roll parameter, let's say. That's for the moment. And sorry, I define it later. But it is another way to call, to express the perturbation around the de Sitter limit. Anyway, you write down the most general expansion with arbitrary coefficients. You insert it here, and you find the projection. But again, you have to be sure that the projection satisfies the condition to be consistent. So you have to work out the Green function of the purely virtual particle, which might be familiar to you because it is the usual formula with Bessel functions, but here the point is that it is unique, so you cannot add arbitrary constants multiplying the solutions of the homogeneous equations. This is complicated, but in two limits, which are the ones that we are interested in. subhorizon and superhorizon, it reduces to the formula that we have seen before, which is sine of some mass times a difference of times, a modulus of the difference of times. Why is that important? So in the subhorizon case, it is conformal time. In the superhorizon case, it is cosmological time. It is important because those are the only ways where you have a connection between the curved background and a flat space in different variables, but you do have, and you indeed find the right formulas for the green function that I told you before in flat space. The point is that here you have a sign always, because instead of the mass you have the absolute value of the momentum, which is positive. But here you do not have something always positive, and you have to require that this square root is real, otherwise you have a hyperbolic sign, and that would be a tachyon in flat space. And since the Hubble constant in the de Sitter limit in this approach is just the mass of the inflaton divided by 2, this is the condition. Okay, so this is where the condition comes from, and this is where the prediction comes from. So R as is bounded by something like 3.5 divided by 1000 and 4 divided by 10 thousandths. This comes from that. And this comes from the opposite limit, which would be an infinite m-chi. So the inflaton mass divided by 4 bounds the mass of chi, which cannot be too light. It should be at least 10 to the 13 GeV, but otherwise it can go to infinity. However, the tensor-to-scalar ratio R does not depend so much on this unknown parameter. So this is an unknown constant of the theory, the additional term with respect to the Starobinsky theory, and we do not know what it is. But thanks to this bound, the prediction is quite precise. So this is the moral of the story so far. And in the last part, I give you this vocabulary between quantum field theory and inflationary cosmology. So basically, the slow roll is described as an RG flow, and the slow roll parameters become couplings. The equations of the background become beta functions. Conformal time will be the sliding scale. The perturbation spectra are correlation functions, and the usual Callan-Symanzik equation satisfied in quantum field theory will be a certain RG equation at superhorizon scales, which is nothing but the conservation of the spectrum at superhorizon scales. Asymptotic freedom is the fact that you have a de Sitter limit in the infinite past. The subtraction scheme is the frame, Einstein frame, Joner frame, etc. Then you have the usual things in quantum field theory: dimensional transmutation, the fact that conformal time drops out of the spectrum, replaced by the momentum. The running couplings and the resumations of leading logs can be used to calculate high orders. However, you see question marks here because this correspondence cannot be used in all models of inflation, but just a subclass of them. And there is a superposition between the RG approach and the potential approach and the F of R approach, but they are not equivalent. So there are cases there that I cannot describe here, and there are cases here that I cannot describe there. A lucky thing is that there is no anomalous dimension, but this is just because we are restricting to superhorizon scales. Maybe if one goes beyond this, you will find. So we consider these two theories. One is usual Einstein gravity with no Weyl squared, and the second one is the one with Weyl squared, always with the Starobinsky mechanism and potential. And how to find this flow. You write down the equations of the background metric, and you will see that you will have to define this coupling alpha as the usual slow roll parameter in the Jordan frame. So even if you use the Einstein frame, you should define alpha as the slow rho parameter of the Jordan frame. And then you find that you can rewrite the equations in a certain way, like this, and you introduce the conformal time, and you can rewrite them in another way again, which is this, the beta function. So this coupling has a derivative with respect to the log of the modulus of time, which is an expansion in powers of alpha, and the first term is negative, like in QCD. You know the answer exactly, numerically at least, not analytically. And then the spectra P satisfy Callan-Symanzik equations because they are conserved on super horizon scales, and this conservation law can be rewritten as a partial derivative plus the usual beta function term. And then you can integrate them, and you can see that the spectra can be written as expansions in powers of a running coupling, which at the leading log order looks like this. And these are the spectra in without y squared to order. So we have, this is the leading order, then you have the first correction, the second, and the third.
And Tomo, I'm getting really confused by this. I understand how to derive the Callan-Symanzik equation in ordinary field theory, but there the couplings are parameters in the bare theory. You're making epsilon, you're regarding epsilon as a coupling. How is that? I would say that's a dynamical variable, not a parameter in the bare theory. Can you explain this?
Yeah, but it's since there is a background, so it depends on some t or tau, you can see that as a running parameter. And formally you have this correspondence. So I'm not claiming that there is a meaning beyond the formal correspondence. It happens that all formulas look the same, and all manipulations look the same, and even the dimensional transmutation looks the same. If you have this alpha of minus tau, you will see it disappear everywhere.
Sorry to disrupt your presentation, but I think I'm probably not the only one confused about this. You're saying, if I understand correctly, that the Callan-Symanzik, the thing you're calling the Callan-Symanzik equation is actually an equation which is true for some other reason.
Yes.
What is it? Is it one of the Einstein equations? Is that it? Or one of the gravity equations?
No, this is the conservation on super horizon scales. So you have to go to super horizon scales, and on super horizon scales you will see, this is a known fact. I'm not claiming that this is new. I just give the interpretation of that in terms of this Agiflow. You will see that perturbation spectra are conserved in the super horizon scales. So they satisfy this. They cannot, you cannot have spectra depending on tau, the conformal time, and the energy. But only in
so it's a consequence of the mode functions freezing in, is that correct?
Yeah, it's a consequence of a limit, basically.
Okay, thank you.
Super horizon limit. But it is valid to all orders in alpha. You don't need to be close to the theta. It's tricky, yes, but the talk I cannot give more details. And in the end, if you want to look at the running inside the data, well, this is it. It will take a while to make measurements sufficiently precise in order to see the difference between the non-running in red and the running curve, because this is taken from Planck. So you see the arrow sigma, and you should be able to appreciate the difference between the two lines in red and black and blue. So that is, here it is emphasized, but if you emphasize it enough, it becomes evident. Unfortunately, it's a long journey to get to this precision, but this is a part of the predictions. And in the case of the tensor spectrum, you have a window of possibilities, because you still do not know what this m chi is, and so it can be from 1/4 of the inflaton mass to infinity, But again, this is very emphasized by the plot. Otherwise, it is a very subleading, very small correction. But it's nice that you can at least compute these corrections theoretically, because in cosmology you do not need loop corrections. So everything is there in this, and it is a classical theory that is quantized on a non-trivial background, basically. So let me conclude. Purely virtual particles are based on a new diagrammatics. They have their own applications in phenomenology, but I cannot talk about those here. Importantly, they can make a theory of quantum gravity based on this concept testable in our lifetime, basically, because you don't need to get to the Planck scale. The energies that are involved in inflationary cosmology are the energies of these masses. But still, the consistency of the model tells you that there should be something more than just the infloton, this m-chi, and unitarity from high energy physics tells you that you should treat it in a certain way. And so basically these are very constrained predictions. If this turns out to be wrong, then I don't know what to do, because I even added a second scalar field to study double inflation, and then you have an RG flow with 2 beta functions and 2 couplings, and it is still de Sitter free, and you can have a perturbative region. Normally you need numerical methods to study 2-field inflation, but you have a perturbative region, and in that region the leading prediction is still the same. It doesn't matter if there is a second scalar. So it appears to be very strict. You cannot play too much with that. And finally, we have seen that you can reformulate inflation as a renormalization group flow, where the spectra plays the roles of correlation functions and obey a Callan-Symanzik equation in the super horizon limit. And this could be extended beyond the super horizon limit to see what corrections you have, or to non-Gaussianities, or to non-trivial curvature of the background metric. This takes a while because it's quite a work. But anyway, this vocabulary allows you to push some calculations systematically to high orders, at least in a subclass of the known models of inflation, because you cannot find this correspondence in all the models of inflation. Thank you.
Okay, thank you very much for your interesting talk. Questions, please. Please raise your hand, or just, okay. Wooder, please. Raymond Wooder.
Hey, thank you for this talk. I'm still confused about very many things. I think probably a lot of people are also confused. In the last comment about the Callan-Symanzik equation, you're taking that from the fact that the mode functions approach constants at late times. I wouldn't say that that's an exact result, right? I mean, they fall off exponentially, but they're never exactly constant.
But yeah, this is the known fact in cosmology. So it's I'm just reformulating it. It's
but it's not a known fact. The known fact is that they fall off exponentially rapidly. You're writing equals 0, right? That's not true.
Yeah. Okay. If you want, you can write equals 0 up to corrections. But the predictions that we make are about the super horizon limit. Those terms that you are considering are even more difficult to test. So yes, you could include them, and then I've not studied what the effects are if you can still interpret the corrections as an RG Callan-Symanzik equation with a mass term. You know, this is quite a simple version of the Callan-Symanzik equation, where you do not have any anomalous dimension, you do not have any mass. So I do not know yet if you can still use this and extend this interpretation by including the corrections. because it's quite hard, and it was hard enough to get here. But you're right. I mean, there are corrections. If you do not want.
Okay,
to
thank you. I have a number of other questions, but I see other people have questions, so I'll sit by and hold.
Okay, thank you. Oh, yes, so next questions from Bob Holden. Bob, please ask your question.
Okay, hi. I just asked about the optical theorem you end up with.
Yes.
It looks to me like it would imply the standard unitarity bound on the size of amplitudes. Is that right?
The standard unitarity bound, which one?
Well, it's often used in
the Froissart bound.
No. To bound the size of amplitudes in the high energy limit, when you say that high energy amplitudes are well behaved, you say that when it satisfies the unitarity bound.
Yes. Now, so here we have something to clarify indeed, and we are going to write something about this, because as we have shown in a paper with Marco Piva some time ago, the point is that the prescription, this removal of lines in the tables, is not analytic. You have analyticity in a new way, in a modified way. So you have that an amplitude has regions of analyticity, but you do not have the usual analyticity. And behind the usual bounds, unitarity bounds, there is the assumption of analyticity, of course. So this is a delicate point, and I agree, it deserves a careful analysis, and we are going to do that. But the evidence, the preliminary results that I can tell you is that the cross-sections are valid up to the Planck scale. Bound included.
I'm interested in the high energy limit, way above the Planck scale.
Oh, no. That there is a sector where I can push the predictions to unbelievably high energy, but that is not this sector. The cross-sections, I cannot push them beyond the Planck scale, and I cannot say what the high energy limit of the theory is. No, I cannot say that.
Okay, but your optical theorem is basically standard in the sense that it's a positive definite, right? That all the terms are positive definite.
Yeah, but the point is that you will have...
That's all you need to derive the standard unitarity bound.
And that will be true diagrammatically, but you will have that cross-sections will be pretty much like in Einstein gravity, expansions in powers of this. Okay, so when the energies are bigger than mass of Planck, you just have m Planck series that you cannot trust. So you are out of the perturbative region. So you cannot say that, claim whether this is positive or negative, because it is a sum of increasing corrections. You cannot stop anywhere here. You cannot truncate.
I mean, I thought the whole point of all of this is a UV complete theory.
No, this is not a UV complete theory. I do not claim that it is a complete theory, and I actually do not think that it is UV complete in the sense of like the standard model, which is a perturbative theory, and it has its certain range of applicability, because you do not know what, even in QED, what can you say about the ultraviolet limit of QED? You can say that perturbatively, all the identities, the optical theorem are true. You can say that renormalizability is true, locality is true. The perturbative theory is always well defined, but sometimes you find series expansions that cannot be resummed, because if you do not know what the coupling of QED will be at high energies, or you do not know what Landau pose will be. So in that sense, yes, but it's still like an ordinary quantum field theory, which has a certain range of applicability. QCD, for example, is good at high energies, and However, whenever it fails, it is just because you cannot resum the perturbative expansion. So there you would have to know.
I would be interested in just the lowest order prediction for an amplitude in the high energy limit, and that should satisfy the standard unitarity bound, which is also you can consider to be perturbative.
Sorry, can I also ask a question related to this? I know there are other raised hands, maybe they are not related to this current question. So I was on a call. I hope I didn't miss the point. But so if we take, for instance, electroweak interaction in the standard model without the Higgs, we know that WW scattering goes like E squared at high energy at 3 level, and if we add an Higgs, so a hard degree of freedom, we can unitarize this process because we will have extra diagrams. When we sum them up, they will cancel this behavior, this let's say E squared behavior. So in the case of stellar theory, I mean, in this sense, I would call the addition of Higgs a UV completion of the standard of the electroweak interaction, because we are unitarizing the process, let's say somehow. Also at higher energy than the energy where WW scattering without Higgs will fail, let's say. Okay. Now, in the case of stellar theory, of course, we have several problems. So in the case of GI, we have several problems. One of them, if we just compare to WW scattering, could be what was discussed right now, that basically the graviton-graviton scattering grows like E squared. Okay. So from a UV completion, where with the UV completion, I mean like adding massive degrees of freedom, which should improve the energy behavior even at 3 level. Okay. What I would expect by adding spin 0 and massive spin 2 is that we get a strictly normalizable theory. So we have a very good, I mean, we know how to control loop behavior and so on, but we should also, I mean, I would also expect that at 3 level, we unitarize the process of, for instance, gravitational scattering. And it seems, from what I understood from also a paper by Bob, is that to really cancel this E squared behavior, you need to add to inclusive cross-section also processes where the external leg is the massive spin 2 ghost.
Yes.
Instead, so in this sense, by keeping the massive 2 ghost as an external on-shell possible state, we can cancel this behavior. In the end, we will get some high energy behavior at 3 level, which goes like 1 over E squared. So which is basically improved. Now here, if we apply the Fakian approach, it's true that we are not modifying renormalizability because we are not affecting the loop behavior. But at 3 level, we are excluding possible on-shell states. Like for instance, we don't want any spin 2 on-shell massive state. But it seems to me that if we remove this, then we do not improve the 3 level gravitational scattering, which will still grow like E squared.
That's true. The question is this a problem? No. This is what I want to question. Because if you say that this is a problem, you have to tell me why you trust this as an exact result above the Planck scale when the first loop correction will be this. And higher loops will be worse and worse and worse. So why do you claim that there is a problem there? You do not know the exact answer. The unitarity bound is satisfied by the exact cross-section, which you don't have, because you are out of the perturbative regime. But in this sense, just one last. In this sense, you would say that basically your theory breaks down at Planck scale. The perturbative expansion, yes.
Yeah, but you see, in the standard model,
some sector of the theory is beyond the perturbative expansion above the Planck scale. Some other sector will go down, but that is not in the scattering amplitudes. You will have to choose maybe some special scattering amplitudes. But in general, a scattering amplitude will have a range of perturbativity that goes from 0 energy to the Planck scale.
But this end is much, is a bit, I would say, if we reason this way, it is much worse than standard model, because in standard model, we would say that the theory breaks down maybe at the Landau pole, the perturbative expansion. But here instead, of course, we'll have some Landau pole. For instance, in your paper, you said some Landau pole can happen at 10 to the 10, to some very high energy. but that's not that's not where the theory would break down. They would break down at
that sector. There is a sector of the theory which is the purely virtual one that remains perturbative up to those energies. But there is a sector of the theory. Basically, there are two power countings. As I mentioned in a paper with Piva, we discussed this fact. Since you are making these surgical operations that distinguish imaginary part by cutting away delta functions and real part, the real part will go its own way and the imaginary part will go its own way. There are two power countings. And one will be perturbative up to unbelievably high energies, but that is not scattering amplitudes, or maybe that there could be some combinations of scattering amplitudes, maybe, but I don't know, because canceling contributions is only possible if you add ghosts. You understand that?
Yes.
Because you can cancel positive things. So I do not expect, but still there is a range of perturbativity always in quantum field theory. Here there are two. Because
it's a bit different from standard model case.
It is different. It is completely different. Yes.
Yeah, because it is that, for instance, some people. I'm just saying. Some people can say, "Okay, listen, I don't want Tachyon. I want to keep the ghost. Maybe have negative norms, like my theory. But in that case, you would still. You see, even with Tachyon, you need to pay some price. In this case, it's this 3-level bad behavior of the.
Sorry. I disagree with the word bad behavior. It's a behavior, okay? Thank you.
Sorry,
let's
bad
not
behavior.
Inject,
sorry, you're right. Like bad behavior at the Planck scale, I would say. Maybe.
I don't regard QED as a bad theory, although I know that.
Sure, I agree with you. But I would say, for instance, QED is good, maybe up to Landau pole. Would you agree with that?
No, the Landau pole is one thing, but you do not know. Where to use it. I don't know where the coupling becomes of order 1 in QED. I don't know.
Sure, one should check that. But
in QCD, when the coupling goes to 1 at low energies, you know that it is not good. Still, it is a very good theory. That's my point.
Sure, but it will be very hedge, right? It will be very hedge. But yeah, I think there is still like some problem anyway at Planck scale here, which should.
I'm not claiming that I want to have anything better than what we have with the standard model, and I'm willing to pay prices because, of course, quantum gravity will have to introduce some prices to pay. One is the microcausality, one is this, but as long as I can make predictions that can be falsified, I'm happy. That's it.
Okay, so maybe what can happen in this case that you should resum all these, as you said, this correction, and maybe, for instance, if you put some, dressed propagator, whatever, this maybe could play some.
Yeah, but it is hopeless. You would have to know the non-perturbative theory. So I find that really difficult because we don't have examples in the standard model where we can go beyond. Well, as you say, there are examples like dress propagators, but with fake particles, I can tell you there are other difficulties there that I explain in some paper, some uncertainties of new type when you try and resum the dressed propagators of fake particles. That should be observable, but still there are something unexpected, new things.
Sorry, Bob, I interrupt Bob, so yeah, maybe you want to continue. But thank you.
Yeah, I'm not sure I agree with the statement that these cross sections just keep getting worse and worse in higher orders, if that's what you're saying.
Yes. So are you claiming that in let's say Einstein gravity? Let's say
renormalizability occurs is good at any order, and I think this will be true in the same way here.
Yeah, but take Einstein gravity.
I'm talking about stellar theory.
Yes, I understand, but to illustrate.
So I think there's a unitarity bound in the stellar theory that you derive in the standard way from the optical theorem in the stellar theory.
I don't know.
Is he using the stellar theory? I thought he was not explicitly taking the negative norm poles.
Yes, exactly. That's a different theory. So you will not have what you have in stellar theory.
But you just keep, I'm taking the stellar theory, keeping the negative norms.
Yes.
You can still derive an optical theorem. That optical theorem does allow E-squared behavior, but no worse than that. And that's a non-perturbative statement, at least in the sense to all orders in perturbation theory. It allows E-squared behavior at high energies, but no worse than that.
And is that you say that it is consistent with unitarity?
That is the unitarity relation in the stellar theory, yes.
Okay.
You just keep the negative norms around and just plow through everything you usually do.
Yeah.
And this is what
so in my case, however, but I will have to study this. I'm going to do this. I expect instead to have these corrections. That's why I claim I cannot say this.
Okay, so this is your theory. Okay.
I'm not claiming that in stellar theory what you say is wrong. I just don't know.
Okay.
Okay, may we go to the next question? The next questions come from Shravan. Shravan, please ask your question.
Hello, Damien. Thanks for the very nice talks.
Hi,
I have a couple of questions actually. So first question is about observations. So as you provided the predictions according to your description, as you said, like the tensor-to-scalar ratio, there is a range, and also for the scalar spectral index, but it does depend on the number of e-folds, which is not fixed from observations. So there is still 50 to 60 range. So I want to ask, what is the prediction for number of e-folds? Can you do it more precisely? But of course, for that you need to apply this for proper understanding of reheating. So I don't know if you have looked into this.
That's why I want to avoid that, because in these predictions, n is just used to convert the slow roll parameter into. I don't find it. So here it is just that. That's why I eliminate it in favor of alpha or the slow roll parameter. But no, I do not have a prediction for n, because precisely the reheating phase will. Well, I still have to study it, but I started, and there are things that I still do not understand there.
Okay. Because unless you fix n, it is very hard to verify this prediction. You say
no. Here you
with
don't
any
need
experiment. Yeah.
No. Here you don't need, because you do not need the reheating. You do not need to push. This is how people normally express the predictions in terms of n. That's true, but that introduces an unwanted difficulty here. You can avoid that. Just use the epsilon parameter and the alpha. I see it as a coupling, right? So for me, this is a coupling. But coupling is not physical. Even in quantum field theory, it's just a parameter. So you have to eliminate it from your physical prediction. And once you eliminate it, you will have the prediction that I told you at the beginning, which is just an equation between other things. But you have to eliminate it. If I use n, I will have to eliminate n, because I do not want to predict n. And once I eliminate it...
Okay. Yeah, you're deriving a relation between r and n. Okay, I see. Yeah, I didn't see this properly before. Okay, I understand. So I have my second question is, you provided this fact and prescription, which solves the problem of ghost from quantum field theory wise. Well, then can you apply to for any theory which has ghost, for example, sixth order gravity?
You can, yes, as long as you have this no tachyon condition fulfilled, so the mass squared cannot change sign, but you can change the sign in front here. You can even make a physical particle fake. You don't need to do this with ghosts. You don't need to have a decaying thing like Levick, and you do not need to be a ghost. You can even question whether the Higgs field is fake, for example.
Okay, so then it's ultimately projected to experiments to say whether it is real or fake.
Exactly.
Okay. Okay. So my third question is again it was related to what I asked before. When you describe the Fackian prescription, you relied on S matrix and unitarity, the optical theorem. But then in cosmological background, these things are not there. So then the route you took is basically with a toy model, and you kind of matched what you get from your equations, and then compared it. Okay, well, it seems to be consistent. Well, there is still something missing to say whether a Fackian is really a Fackian in a curved space-time. So, from the point of view of the standard QFT techniques, are the modified QFT techniques you explained. So, well, I would like to know your comment about this.
Yes. So don't rely too much on these toy models. These are just a way to introduce the thing for the talk, because otherwise I find very difficult to explain the many manipulations that you need to know to do in cosmology, unless you are really an expert in, you know, every meaning of the formulas that I write. But and nothing relies on those toy models. Those are just to explain everything. You can follow the entire construction within inflation, and it's quite involved but heavy, but you can do that. So.
Okay. Can we go to the next question? The next question is from Philip. Philip, please ask your question.
Okay. First of all, Daniel, Damiano, thank you very much for your talk. I have a comment and a question. The comment is, I'm inclined to agree with you that whatever these fake particles are, they don't have a classical limit in the following sense. If I write down a Feynman path integral, which is an integral over classical paths, it gives me the quantum mechanical time-ordered product. And the time-ordered product has the standard I epsilon. So whatever you're doing cannot be reached from a Feynman path integral. So at least in that sense, you can say it doesn't have a classical limit. However, dropping delta function might give you a problem in the following sense. If you look at the vacuum polarization, you've got a q squared photon coming in, you have a fermion loop, and then a q squared going out. And that graph has a branch point at q squared equals 4m squared. Mm-hmm. And there's a discontinuity across it. And what I remember is the discontinuity is generated by the I pi delta functions in the two internal fermion lines. And so even though the discontinuity is in the momentum of the external photon, you need the standard I epsilon prescription for the internal fermions in order to generate the discontinuity in the first place. So it seems you might be losing that.
You are exactly right. You got the key point, actually. So let me review this is the key thing. Because it's true that this is the three-level propagator. You just cannot use this inside diagrams. You cannot. You have to be guided first by the Feynman prescription. In the first part, what I didn't emphasize, so my fault. Here, you use the Feynman prescription. Everywhere. The usual good I epsilon. Here, here, here. Only here you make the modification. You need the Feynman I epsilon prescription for 0.2, for example, which is the integral on the loop energies. And this is crucial, otherwise everything is gone. And that's where you generate the cuts you are talking about, which are in these two, two deltas. And then if you drop the deltas, you have that, because the cuts, contributions are both from here and there. You eliminate a contribution and you will still have a cut, but instead of a cut, you will have to basically enlarge this cut into a separate region, and that's why you do not have analyticity, because you will have function 1 here and a function 2 above the threshold, which is the reason why you don't have analyticity. But you still have this crucial point, and since you are just interested in the real axis, it appears as it's a cut, but actually it is a different region.
Okay. So in that case, you can say what you're doing has no effect on renormalizability.
Yes.
That's completely standard. The only issue is what's the discontinuity across the cut in the physical region. And that's basically what Bob Holden was asking you about unitarity. And that's why it looks puzzling that you can retain unitarity.
Unitarity is this table, which
Yes.
I split into many things. And so the way I prove it is that since I eliminate rows, entire rows, which are separately zero, I eliminate zeros. I eliminate zeros from the optical theorem. That's why I retain unitarity. If you have to do it consistently in all diagrams and in all amplitudes and in all aspects of your theory, otherwise everything will collapse.
I mean, I understand that, but there's more to unitarity than the optical theorem. I mean, every time you have a discontinuity, every time you have a branch cut, the discontinuity across it has to be positive. I mean, that's a stronger statement about unitarity.
Yes, but if you have a theory with potential ghosts, sometimes you have wrong signs. I can say I eliminate those and only those. But if you do it consistently like this, then you get an optical theorem.
Okay, as long as your discontinuities are positive, even if they're not the same value as in standard with no fake particles, then I think that's fine.
But also if it is negative.
Negative, I would say, is not fine.
Because you just remove it everywhere. Everywhere it appears, in all diagrams that contribute to the optical theorem. And
well,
so
I mean,
it doesn't matter whether it is positive or negative.
It's not accidental that in standard Feynman diagrams, the discontinuities across branch cuts are positive.
I agree.
It's not accidental. It's driven by the plus I epsilon prescription.
Yes.
Yeah. Okay.
Here I'm claiming there may be some minus in the front of a propagator, right?
Yes.
So you do not change the I epsilon, but just
if you take the propagator 1 over p squared minus m squared plus I epsilon.
If you change the sign
here
without touching this, you can go through the entire diagrammatics and you will have potential minus. In the bubble you don't see because you have 2, but in the triangle you start seeing. You can have a minus sign in front of one propagator only, then you will have a minus sign in front of some delta functions because...
Okay.
Okay. Next question. One more question from Luca. Luca, please ask your question.
Yes, thank you. So before asking the question, just to go back to the previous point, just very quickly, the one that we were discussing. So, so in this, I mean, so you said in your talk that this way to quantize gravity with starting from stellar theory and then using the Feynman prescription is, let's say, it's very close to what we usually do in standard model because we try to keep locality, normalizability, and unitarity. But I mean, do you agree that somehow we are anyway paying some price, which is besides like violation of causality and so on? We are paying some price even in some sector of the theory. We are anyway not improving what GR was suffering from. For instance, this 3-level behavior of the scattering amplitude? Or do you think is something that anyway should not worry in general because there should be any reason?
That may be true, but if I can make predictions up to the Planck scale in some other sectors above, and I have a unitary theory that satisfies all the axioms and the properties of the perturbative expansion, and perturbatively you can of course go beyond any energy range or any limit, term by term, you just cannot resum the series, then it seems to me that it is more or less like the usual problems of the standard model. Yes, here you have powers of the energy divided by the Planck mass, and not just powers of the coupling. But as long as I can make predictions that can be falsified, I don't.
Sure, no, I agree with that. Indeed, for instance, cosmology, you're making predictions. But for instance, if you want to just study, like, I don't know, some graviton scattering, transplanking energy, with your approach, can you do that?
No, I think that above the Planck scale, you will have the sum that I told you, and so you cannot, unless you know the non-perturbative theory, you have can calculate the series to all orders, to any order you want, but you don't know where to stop, and there is no way to make sense of your predictions because the corrections are larger, that you are missing are larger than what you are considering. So that's the situation.
But one thing I should maybe stress is that in the case of just stellar with negative norms, where you can improve even the 3 level.
But you can do that if you sum certain things in the initial states, right?
Sure. Because maybe in that case it could happen that your theory is telling that above some edge you cannot neglect some states, for instance. I mean, some states. So, I mean, it's good maybe to anyway emphasize this distinction when we just take, like, for instance, the ghost as an on-shell state, because anyway, some cancellation that you have even at 3 level, and maybe there you can really study some scattering or even transplanting somehow. Of course, there can be other issues, I don't know, but. And okay, so I only had one more question. Like, as you said, the starting stellar theory is just a starting Lagrangian, but it's not the real classical Lagrangian through which we can make predictions, for instance. But for instance, if you want to just compute in stellar theory, if you want to compute, for instance, the gravitational potential induced by a point-like source, in that case, we have just Newton plus 2 Yukawas. In this case, would you still have the same after projection? Or?
Yes, because whenever time is not important,
that's
the projection is trivial.
Okay, and actually, just a comment.
This is the purely virtual part.
I see.
So it's the same. It's a Euclidean.
Just a comment. So, for instance, if you take just the still potential with the Newton plus 2 Yukawas with the m phi and m chi in the exponents, and you impose that the potential is always negative, even at r equal to 0. What you get is exactly your bound, like m chi greater than m phi over 4. So maybe, I don't know, there could be some, just a comment.
I see.
But just by imposing the phi is always negative, even at short distances, you get really, I mean, that kind of inequality, that m chi must be greater than m phi over 4. So it's just a comment. You can,
I didn't know that.
Yeah. Maybe there could be some relation, some physical meaning about this bound. Could be like.
So, do you think there is a meaning?
Sorry?
Do you think there is a meaning why the potential?
No, I don't know. Maybe there could be. I mean, just the impose that phi, the gravitational potential, is always negative. You get that inequality. Now, I don't know if there could be some deep meaning, but I was just.
Okay.
Yeah. Okay. Thank you.
I see one more question from Woodard. Please ask your question.
Okay, thank you. One of the things that confused me so much about your talk is that it seemed to have 2 sorts of parts. The first was talking about flat space diagramology, and the second part was a purely classical analysis of the Eddington plus Weyl theory. Would it be fair to say that what you're doing is just solving the r plus r squared plus c squared theory regarding the c squared term as a perturbation? Would that be a fair statement?
No, that is the crucial point.
In what way is that not correct? It seemed
Yes,
to me
not,
very much like that was exactly what you're doing,
no,
at least in the second part.
No. That's the crucial thing. Because if you do that, then you don't get the prediction. Because that thing you are saying is the expansion around in powers of m phi divided by m chi. You are basically treating the y squared term as a perturbation, so its coefficient, which is 1 over m chi squared, should be large. But then you don't get this denominator, which is crucial.
Well, in turning off its degrees of freedom, it seems to me like you are, and working around solutions.
No. This is the crucial thing of fake particles, that it allows you to cross that bound. Maybe you cannot cross the Planck scale for another reason in a certain subsector.
But if you're not treating it as a perturbation, how does it not have its own degrees of freedom? It would have
because
extra
of the
degrees
prescription.
of freedom, right?
No, because of the prescription. That's the crucial thing of the fake particle.
Because of the prescription.
You cannot even
the
have
analysis
boundaries.
that you presented, where what you wanted to do was to just redefine the theory as what you would get if you used perturbation theory to localize the Lagrangian. That is just by definition treating the c squared term as though it's a perturbation.
But that is not a perturbation in low energy expansion. It's not a low energy expansion. It's a perturbation.
I wasn't talking about low energy. I was saying I was very precise, treating the c squared term as if it was a perturbation. I think that is just exactly what you're doing. And all of this stuff about diagrams, this is just confusing everything.
So what do you mean that this is a perturbation?
What you're doing, when you talked about taking the Lagrangian and simplifying it,
yes,
to eliminate the higher time derivatives, and you meant of the Weyl squared term, presumably not of the R squared term, because that is the inflaton field in the Starobinsky mechanism. You are just treating it as a perturbation. That's the definition of treating it as a perturbation.
There are some places where what you do is equivalent, but you're not doing that. So let me see where to.
Show me one. I don't see any one. In terms of your model, the point particle model that you gave, where you eliminated the higher derivatives by using regarding them as perturbations and using the lower derivative equations. That's just definition of treating the Weyl squared term as if it's a perturbation.
Well, there is the fact that here the expansion in powers of lambda and this part talk to each other, so that may be confusing. But then there is the condition for applying this.
Well, you're right, it was confusing, but I think I've understood it, and I think it has a very simple way of a simple explanation.
Check this, for example.
Well, you don't agree, so
no, check this.
Let's not argue about it.
No, sorry. Let's argue about it. So if you
okay, so it seems to me that if you don't treat the c squared term as a perturbation, then you will get extra degrees of freedom from it.
No,
this I don't think is arguable.
No, because of the prescription. That's the entire point.
But the prescription amounts to treating it as a perturbation. Now you can say, well, I'm treating it as a perturbation in some other sense. Okay, fine, but you're still treating it as a perturbation.
Then I ask you, where is the perturbation here? Because here I have this green function, which amounts to integrating out the Facon. So at 3 level you have external particles that are physical, for example, the graviton. And indeed, internally you have the fake particle. You have this green function.
Treating something as a perturbation doesn't mean that it doesn't affect physics. It does affect physics.
I know. But so I'm asking you.
It just means that you don't have initial value data associated with it. You don't have particles associated with it.
Yes, okay. I'm asking this question.
And in terms of the question you just asked there, where treating it as a perturbation theory matters is that you don't have a pole from chi mu nu going on shell.
Yes. One way to get rid of poles like that is a low energy expansion. I understand. But this is not it. So my question is, I have this square root appearing in this green function. Can I use it exactly in keep it exact, or should I expand in m chi large in your definition of perturbation? If you can use it exactly, then maybe our notion.
Well, in my way of setting it up, it would just be you take the c squared term and you regard it as a perturbation. So you solve the equations of the r plus r squared theory. Those are the zeroth order equations, and then you evaluate the c squared term at those solutions, and resolve the for the first order corrections, et cetera, et cetera, et cetera.
Yes, then you lose this information because you.
Well, I sure don't see how.
Because you should expand, as you just say, this expression in powers of m phi divided by m chi. I cannot.
What is m phi and m chi in terms of the fundamental parameters of the Lagrangian?
Yes.
So I'm just saying that you treat the c squared term as a perturbation. So your zeroth order equation is just r plus r squared equation.
Yes.
And the c squared term is absent. Then you solve that. That gives you the zeroth order field. And I think that must be true just based on degrees of freedom.
There are some things
and the first order.
There are some
first order correction has come from evaluating the c squared contributions at that solution, and then regarding them as a t mu nu that you then solve for a correction to the original variable, the metric, et cetera, et cetera, et cetera.
There are some things that may coincide with what you obtain by doing that, but if you do that, you miss the other thing, including the crucial thing that gives the prediction, because you are treating this as a perturbation. So this is m phi, and this is m chi. What you're doing is an expansion in m phi divided by m chi. Okay?
I would not say that. I would say I was doing an expansion in 1 over m chi.
Yeah, but this is dimensionful, so what does that mean, 1 over m chi?
Well, you're talking about a field theory, and field theory has parameters in it. The solutions would have parameters in it. For example, in cosmology, there'd be a Hubble parameter, et cetera, et cetera, et cetera. Yeah. There are momenta of particles, et cetera, many, many parameters. Yeah. The key thing is that your all the corrections are in powers of 1 over chi.
Yeah. So m chi, the Hubble parameter here is just the inflaton mass divided by 2. So if you expand in powers of this,
I'd say there's an infinite number of parameters, but all of them are going to have, but the corrections to your solutions could all be written as something that would be a solution in Starobinsky inflation, plus something that goes like 1 over chi.
Exactly, but you see that this is not it. Check this formula. This is not the Starobinsky 1 plus corrections divided by over 1 divided by m chi. You have an exact expression here. And this is crucial to check that the prediction doesn't change so much in the entire range. And it's also crucial to find the bound, because you can never find a bound here if you expand like this, if you expand in around m chi equal to infinity, because it will always be true.
I think that is the Starobinsky prediction in 1 over chi. If you take chi to infinity, m chi to infinity, that's 1 over n squared. That is the Starobinsky prediction. Or 12 over n squared, or 6 over n squared.
If you take m chi to infinity, you get that, yes. But you don't take x.
So that is the Starobinsky prediction. That what you're doing is a perturbation expansion of the
Look,
around
I'm
Starobinsky.
sorry, I don't understand where is the expansion here. This is
M chi is a big number, right? So if you
No,
take M chi
no,
to
M chi is
infinity,
not a big
you
number.
get the zeroth order result. The zeroth order result is Starobinsky inflation.
M chi is not
if you
a
then
big
look
number.
at,
M
I'm sorry?
chi could be as equal as M phi divided by 4. It's not
But,
necessarily.
the perturbation series that you're doing is an expansion in powers of 1 over M chi, and I can write that,
And that is
expansion
false.
that
What
way.
I'm
It's
doing-
easy to do it. Just divide the numerator and denominator by 1 over M chi squared. Then you have, 12 over n squared times m sub phi squared over 2 m chi squared, and then expand in 1 over m chi squared. It's easy. And what you get is the first order prediction, which is exactly Starobinsky, plus corrections. That's, I think, what you're doing.
No, I'm not expanding in powers of 1 over M chi, and I do not need to. Some things...
Okay. I think it's probably clear to everybody else.
Some things can coincide with the expansion because for some things there is a finite number of contributions. So in that case you can expand or not, it doesn't matter. But there are key things like this that are not expanded because I do not have this expansion to make.
But the one you showed me, R, really is, it can be written as a series expansion that starts out as Starobinsky plus corrections, right?
It can be, yes, it can be. But what does it,
okay, so I think that's the easy way to say what you're, if I were giving your talk, if I were presenting your model, I would just jettison all the diagrammatic stuff that just confuses people like Bob, who are looking for an ultraviolet complete theory, and Luca, who are looking for an ultraviolet complete theory and looking for some comment on Stelli's theory, and state that you're treating the c-squared term as a perturbation. That's, I think, what you're doing.
Yes, I'm not doing that, and I do not understand why you claim that. So, again...
Well, because you don't have any extra degrees of freedom associated with it, because I can see from your classical equations of motion that that's what you're doing. That's why I say it.
Yeah, okay. That's the entire point.
Okay.
That's the entire point of the prescription. That's precisely to remove a degree of freedom without the low energy expansion.
I don't think I was talking about a low energy expansion.
Large mass or low energy, sorry, is the same. So okay.
The coefficient of the 1 over c squared term is being regarded as small.
No, it is not.
That's the expansion.
I am removing a degree of freedom without a large mass expansion. Okay? This is the point. I am removing a degree of freedom without a large mass expansion.
Well, maybe we should just agree to disagree on this.
Good.
Okay. Okay, still we have 2 more questions. Bob, please ask your question.
I just wanted to clarify a bit more. So I think your statement is that you cannot use your optical theorem above the Planck scale?
No, you can, but it is a diagrammatic set of identities that are true term by term in the perturbative expansion. What I cannot is make statements about an exact cross-section that needs to include corrections that are larger and larger and larger in some situations. That is beyond the perturbative expansion. But term by term, the identities are always true.
Okay, well, let's just talk about the lowest order then.
Okay.
It seems like you would have the standard unitarity bound on the lowest order result.
Yes, that is fulfilled, because if what you're talking about is valid up to m Planck, then this is smaller than 1, so your bound is satisfied because it's smaller than 1.
Well, here again, you're saying something is breaking down above the Planck scale.
What is breaking down is that you have your infinite series well defined, you can calculate all the coefficients, this and the others, and you just don't know what the sum is. What breaks down is the perturbative expansion.
The question is there a unitarity bound that can be derived from your optical theorem?
I do not know. I don't think you can derive any non-perturbative bound because you just have a perturbative theorem.
Just a perturbative. I'm happy with a perturbative bound.
Well, if you know that these things, as you say in your case, do not appear, then maybe you can do something. But here they do.
But I'm saying that even the E squared term here is not compatible with your optical theorem.
It is. E squared is compatible.
The amplitude then goes like E squared.
Yeah, but it doesn't go to E squared up to arbitrarily high energies because you cannot cross the plane.
Again, all of a sudden you're saying let's not go to very high energies. I want to go to very high energies.
Yeah.
And then if the optical theorem applies, then there should be a bound that says nothing can grow as E squared.
Yes. So if you go to high energies, you will have a perturbative expansion of infinitely many terms like this. Suppose you can compute all of them. You will have to resum them in the exact function of E. And that function may well decrease, like in string theory. You know that you have infinitely many powers that sum up into a very good function, and it may well decrease. Why not? Exponentially, by the way.
But just going back to the tree level result, I just don't see how things are consistent here.
Okay. Can we go to the next question?
Yes.
Okay. The next question is from Dimitru. Dimitru, please ask.
Right. Okay. Thank you very much for the talk. I want to comment on the previous question, Professor Woodard, and I seem to agree with him that actually ultimately what is being done is a perturbation to the value of R by the C-squared term, by the Weyl tensor term, to R plus R squared. And the expansion would not be in 1 over m chi. The expansion is in m phi over m chi. And I think that if you look, Daniel Baumann has computed the correction of Weyl tensor to R. And in the paper, I sent it on the chat, 1507.07250. You will find it there. And I haven't checked the numerical coefficients as the expansion, the first term in your expansion in m phi over m chi is the same, but it looks similar.
Okay,
so in that, yes.
So my question is, I have this formula, okay?
Yeah, you just take the limit m chi much larger than m phi.
No, I don't take any limit. I just have this formula.
I'm saying that in that limit, your result is the one by Daniel Baumann.
Yeah, okay. But
so
I do not take that.
If I took just this relation, you would simply mean that C with the Weyl tensor squared term is just a perturbation to R plus R squared. Now, of course, you have an exact formula, so I don't know. I don't remember the details in the paper of Daniel Baumann whether they could have exact result as well. But I think this has been known. So, okay, that was just a comment. The first question would be that we also have a Higgs, which you cannot forbid the coupling, a non-minimal coupling of it. That would bring a significant correction to your prediction for R by the non-minimal coupling to R. That will change your prediction for R. Do you know how it will change it?
The Higgs. I consider the model of two-field inflation with a second scalar but now I don't remember what.
What's your non-minimal coupling then?
Yeah, I don't remember if there was a non-minimal coupling there. Maybe it will, but you know, it's a parameter that you do not know.
Well, but I wanted to know whether it goes there, in what direction it goes. Is the Starobinsky limit an upper limit to your value of R?
Here, yes. Yes. The upper limit is the Starobinsky limit.
How do you know if you don't know the sign of the non-minimal coupling?
Ah, okay, no. Here, in the non-minimal case, I don't know, because I've not studied the non-minimal coupling. You mean a second scalar, right? Because this scalar cannot have a non-minimal coupling. You should.
Well, it's the one that you have not, but I mean.
Yeah, you could include the.
You extract it from Weyl tensor squared, and while the one in R squared is not, so it doesn't have one. But you cannot forbid the Higgs coupling.
Yes.
So take it this way: I take R squared plus a non-minimal coupling of Higgs, and I get the same result for R as you do.
Yes. So there probably you have some effects if you assume that the non-minimal coupling is large enough. Probably I do not have. The only thing that I've done with the two-field inflation is to show that with two fields, which you normally have to treat numerically, but at least there is a perturbative region which you can treat in the language of the RG flow with two couplings, and there, in that perturbative region, you still have this prediction with no effect. But I am positive that even with a generic scalar, even if it had even without non-minimal couplings, you can affect the entire prediction if you are outside of the perturbative region. Probably, yes.
But I know that if I added a psi R H squared, then the value of R would be shifted downwards by terms toward the psi.
This I don't know.
Psi or psi squared, I'm not sure which one. Anyway, but what I'm trying to say is that correction is of order 10 to minus 3. So it's significant. It's of the same order as the one, I mean, we are talking about very small values here. It is of the order of the precision of future measurements of R, which is 5, 10 to minus 4.
Yes, but you have to assume that psi is of order what, 1?
No, I can tell you. Well, this has been calculated by various people. One is by in a different setting, but anyway, the message is that for perturbative non-minimal coupling, you can the value of R is reduced in Higgs when you have a Higgs non-minimal coupling. It doesn't have the Higgs is not the inflaton. It just sits there and it, in a sense doesn't do much, but it has an impact on R. It's not the inflaton itself. Okay. Inflaton will still be as in Starobinsky. Mostly there is a very small mixing, but that's another matter. The second question is about UV completion. Since you consider Weyl tensor squared, which is conformal, why don't you just impose? Because you mentioned once gauge symmetries as a guiding principle at some point to have UV under control. You could simply gauge the dilatation symmetry, and that brings you to Weyl geometry. And the action that you wrote is very close to that. If I just wrote R squared in Weyl geometry, it has on top of it the Weyl tensor squared, and that is invariant under gauge dilatations. And that, obviously, the ultraviolet behavior is much more under control because it doesn't allow you to write any higher derivative terms suppressed by any scale because you don't have a scale, because a scale is generated dynamically by the spin 0 degree of freedom in R squared term. So if I take just Weyl geometry, no matter at all, what you can write there is R squared in Weyl geometry, which is Weyl gauge invariant. This R squared is usual R of Riemannian geometry plus some function of the Weyl vector, the gauge boson of dilatations. And on its own is invariant, unlike in Riemannian case, under the gauge dilatation, just like Weyl tensor squared is. And that's pretty much everything you can write, apart from if you had matter, you can add other terms. But if you don't have matters, that's all you could write in Weyl geometry that respects the symmetry. So you have a gauge symmetry which respects it, and this and what happens is spin 0 mode in R squared is eaten by the Weyl vector. Sorry, I forgot to add. You also have a kinetic term for this gauge boson of dilatation of the Weyl vector, an F squared. So this F squared, this Weyl vector becomes massive by eating the spin 0 mode of R squared, and you generate Einstein gravity. While at the same time, you still have the Weyl tensor squared, which has all the benefits that Professor Mannheim and Tal have discussed. And at the same time, you don't have any high derivative terms and all these complications because you don't have a scale to begin with to suppress them.
I see. And this is normalizable?
That's a good question. At one point, I talked to Kellogg Steele, Professor Steele, and all this theory would have on top of his original theory is just a gauge boson which becomes massive by Stuckelberg. And that cannot be, they cannot make, this Stuckelberg mechanism is valid to all orders, and it cannot affect normalizability, I think. But of course, there is the same problem that you have a Weyl tensor squared, so you still have the unitarity issue. I mean, it's renormalizable probably, but not unitary. But on the other hand, to begin with, you cannot just write arbitrary terms in curvature that could bring you corrections. And what's important here is that you can go above the Planck scale because the Planck scale is generated by this spin 0 mode of R squared.
Yes.
It's just a vacuum expectation value. So Planck scale is just a phase transition scale. It's natural to have fields, but also energy is larger than the Planck scale.
Okay.
So in this sense, I think that what you do, what I'm trying to say is that you would probably, you could probably do the same stuff that you did, but in the Weyl geometry context where you have a symmetry that would protect, that protects the ultraviolet.
And this symmetry is not.
Sorry.
It's this Weyl symmetry that you have is not anomalous.
No, because the nice thing is that this Weyl vector has been known since 1980s by Taikiro Kugo, who shows that if you took Fermions action, it has the same form as in conformal gravity. It doesn't depend on the Weyl vector because the spin connection dependence on the Weyl vector cancels the covariant derivative dependence on the Weyl vector that you have. So fermions do not couple to the Weyl vector. Gauge bosons do not couple unless you go to some very subtle discussion about the coupling between hypercharge and a Weyl vector of dilatations, which is mixing internal symmetry and external symmetry, space-time symmetry, but is not forbidden by Coleman-Mandula theorem because both symmetries are spontaneously broken, and you also always have a direct product of U1 of hypercharge times dilatations. So that is fine. But anyway, so let's say gauge bosons do not couple. So the only field that couples to the Weyl vector, this gauge boson of dilatation, is the Higgs. And somehow it's expected because it's a gauge boson of dilatation, so scale generation ultimately, and scalars fills that, Higgs fills that. So, but again, I'm trying to say that the analysis that you're doing with respect to the Weyl tensor squared, you should probably do much better if you try to do it in a Weyl geometric context. Okay. So instead of taking r plus r squared that you had there in Riemannian geometry, just take r squared of Weyl geometry on top, because the Weyl tensor squared term that you added is also in Weyl geometry present. On top, you have an f squared of Weyl vector, but there's not an instance here, because that will become massive of the order Planck scale. And Planck scale here will be generated by the web of the field. So you will be able to go above the Planck scale very easily. You have a UV completion. That's what I'm trying to say.
Okay, let's go to the next question. The next question is from Alexei Starobinsky. Alexei, please ask your question. Are you here? Unmute yourself. Okay.
Yes, okay. But thank you. It will be rather a comment inspired by the previous questions, because there were some statements about what happens with R, with small r, with the ratio of tensor-to-scalar perturbations in case we have Ricci squared and non-minimally coupled scalar field. The statement is if this actually the exact result is the following. So if we have if this if the scalar field has asymptotically the Higgs potential lambda phi 4 and coupling constant is large and its signs opposite to the case of conformal coupling, then the result is exactly the same as both in my model and in the limits when m high much more than m phi, namely 12 divided by n squared. But it's possible because the question was, is it possible to have, in this model, is it possible to have a larger value of R? Of course, it's possible for if psi is of the order of unity, and when this second minimally coupled scalar field is in fact the inflaton, but in this case we just returned to the lambda phi 4 model, which indeed produces large R, which is excluded by observations. And my second remark, I think, just regarding the doubts of Robert of predecessor Woodard. I think because I think that speaking about perturbations, he means, my impression that he means that indeed the results can be justified in case of m high is much less than m Planck. But here we have m phi and m high, and so though and if both masses are much less than m Planck, and in case when m high is much more than m phi, then our observations require us that m phi should be much less than m Planck, and actually the m Planck m phi squared divided by m Planck squared should be just approximately equal to the inverse that value of the scalar perturbation spectrum. And so returning to the comment of Professor Woodard, still if the formula is perturbative in the parameter m high divided by m Planck, it is not perturbative in this ratio of m phi to m high. So it's another parameter for which indeed it's well possible to have some non-perturbative results.